please take out your document where you write these down. Remember, last quarter you got a grade for these. There really is no excuse for having an incomplete GLQ because we go over the entire thing in class. So now it's not time to doing mastering activities anymore. It's time to be doing this. Let's begin. All right. So we actually already spoke about the first question here. By the way, because I can basically not see in this suit, I must feel with the force. By that I mean you guys need to help me out with the questions, because I actually can't see them at all. Dynamics of FRQ? Yes. Please stand by. This person wants to try to show me that he knows the ways of the force.
Keyword on try.
I need your seat, Amanda. I need your seat. Tell them that whatever FRQ is, any part of the FRQ that's not about dynamics will not count against them. Right? So, Mike, those are your questions. If there's anything in there that's not dynamics, it will not account against you this time. Is that clear? I think one of your questions goes into a rotational inertia. You don't have to worry about that. Right?
So basically like the entire package that I have.
Basically, everybody's graded, so don't even do it. All right? Put everything else away, please. Everything else away. Only the FRQ and the papers you're using to write. All right, so we actually already, where's the sigils? Can you collect them all? And put them in a stack right in front of you. All right, so we actually already spoke about the first question. The first question was, why is it using dynamics, explain why objects of different mass fall the same way. You guys okay with that? So when we did kinematics, we did free fall. I explained that if you have the same mass, or the same object, different mass, still have the same acceleration, and that's why they fall the same way, same g, right? But we already, just leave it right there in front of you. I already actually explained this, right? So then all I need really is someone to talk about it. Who's this person? Who? You? All right, really. So then think about it. So I have a heavy object and a light object. Now, when I say something is heavy, William, what does that mean for you?
They have a lot of inertia.
Very good, I like that. But actually, when we mean the word heavy, are we really talking about inertia or are we talking about something else?
Maybe mass.
Not really mass even. What are we talking about?
No,
No, wait. Yes, razor. Dixon is getting labels every time you get something right. There's 3 labels so far. Right? The Lego boxes, where are they? You got it? Right. So where were we? You're saying that heavy means what? Wait, guys, are you with me? Pay attention. So heavy means weight, right? But notice how he actually equated weight to inertia. Guys, no side talking, please. Physics C students. So he equated weight to inertia. Well, what's the expression for weight? What is weight? How do I figure? Times? Mass times gravity. Very good. Lautaro. So if weight is mass times gravity, what makes an object heavier? What could make you heavier? Okay, but is there any way for you to become heavier? Yes, there is. Think about it. You can do 2 things to become heavier. If weight is mass times gravity, there's 2 things you can do to become heavier. What's the first thing? Yes, I was saying your weight is your mass.
But like this one doesn't.
Yeah, no, I'm talking about your actual weight. Aside from you holding something, what do you do? It's obvious. But if you're a girl, maybe it's because you're not. I mean, that's actually a subject. I take that back. Everybody worries about their weight. What are we doing when we want to lose weight? All right, what are you losing when you lose weight? Sure, you're losing mass. Stop asking for it. Who answered for them? Who dares answer for another student? He's always been a bad child. Maybe it has something to do with his daddy. But now, in all seriousness, you can add mass. So you can also do what to change a person's weight? Anybody hands up? Yes? Because can you increase the gravity? In fact, it's very easy. All you have to do is walk towards the pole. Because the earth is not actually flat and not actually a sphere. It actually, the top and the bottom of the earth are a little more kind of smothered in. Which means that the poles are actually closer to the center of the earth. So if I wanted to feel heavier, what could I just do? Live in New York City, very good. If I live in New York City, I would automatically be heavier. Because it's closer to the pole. So you know when people talk about Miami being a city where everybody's fit and stuff? Well, first of all, they haven't been to Hialeah. But the second thing is that it's true because we are actually lighter here in Miami because we are closer to the equator than the other states, right? Even better than that would be Hawaii, which is actually tropical, right? So it's going to be at the equator. What is the place in the earth which will be the lightest, you think? The lightest place on the surface of the earth? The equator? But where in the equator? At sea level? Or maybe on top of a mountain? A mountain. So actually the Andes on the equator are going to be the highest mountains in Ecuador are actually going to be the places on the earth that are going to be the lightest. Now, when you go to orbit, do you still have weight? Well, let's think about it. Do astronauts still have mass?
Yes.
Do astronauts still have the gravitational pull of the earth acting on them?
Yes.
Absolutely. So do they have weight?
Yes.
And yet they feel weightless. So that brings us to the next thing, which is the difference between weight and apparent weight. But we still have not answered the question that actually was posed. Using dynamics, why are objects of different weight going to fall the same way? Now, if this object has less weight, are we talking about the different amount of... I can see you, hold on. But it's just, I'm asking a question, so wait. Wait while I ask the question about weight, okay? Right? So what I'm actually saying here, if I have just two objects, is their weight different because the acceleration of gravity is different? No. So why is their weight different? Because the mass is different. Very good. So they have different mass. So this one will give a legal. So this one will have more mass than this one. Now, if that's true, and this one weighs more, which object is attracted or attracts the earth? It's, third law says it goes both ways. More. This one or that one? The cone or the thing? The cone, right. So the cone has more force, and yet it falls at the same rate as the other object. Why is that? Well, why? In terms of dynamics. We talked about this already. Because mass is greater, and therefore this one, even though it has more force, it also has more inertia. Now, what is acceleration according to dynamics? What's the formula for it? Acceleration equals what? Force over m. So even though the F is bigger, the m is also bigger, which actually makes A be the same. Does that make sense to everybody? All right, that's the answer for number one. How can I help? No problem,
And
please.
pictures for the yearbook, because clearly you're going to be in the yearbook.
That's fine.
A daughter, if you're out of uniform.
In fact, let us take this opportunity to stand here, if you are out of uniform, in front of the blackboard to take a picture of physics honor students in costume. Let's do this. I also would like to do a costume contest. And those that have the best costume today will earn a extra label. Come on, anybody else in physics honors in costume?
Pictures for,
I have my 8-foot long with 1 second.
hey, no props. All right, outside, no props.
Can you take a picture for me, please?
I'm getting
I'll do it right here. Wait, you taking him outside for a picture?
Yeah.
Okay, that's fine.
I'll watch your class, don't worry.
That's fine.
I'm taking that. Them. We already did that.
So we're not even trying to do this, we're just gonna like go straight.
So hold on. If you have a custom, please stay here in front of the blackboard. If you have a custom, please line up in front of the, I'm sorry, I can't see anything. Come on, Chris. All right, round of applause for the dogs.
The cows.
We let the dogs out, right? Okay.
Raymond
Very good, very good. Lot of applause for the law enforcement agent.
Right now.
Rest of the dogs again. Dogs, sit. Sit.
If you give me tips, I'll
Sit. Okay. Round of applause to the Native American.
That's
What are you exactly?
He's a warrior.
What? A barbarian? Never mind. She's a barbarian. Hold on. Apparently she's a horny barbarian. She has horns.
Oh my god.
Susan.
And she's wearing things that look like hugs.
Oh, no.
No, those are
Raise light.
I don't know. Either way, let's have a round of applause for the barbarian. Law enforcement. Barbarian. I feel like barbarian, you were rejected. I'm sorry. Okay.
Okay, you
All right.
Even though you.
Zombie convict. I'm sorry, law enforcement has been rejected. All right. I don't know exactly what to call him. I'm going to tread carefully.
He's a ringleader.
Let's go with a ringleader.
What are you supposed to be?
A ringleader.
He crosses.
You are a liar and a spy and a member of the Rebel Alliance. Give him away. I'm just kidding. Let's do a round of applause for the ringleader. Convict zombie. Ringleader. And the winner is... Obviously, I'm not part of the game. I will always win. They have no chance. But I think the ringleader shall get today 5 extra leaves. Very good. All right, everybody.
My mom.
It is hard to believe you had a mother. You see,
It's okay. I don't have mom.
my whole problem, I went to the dark side because of my mother, if you really think about it. Right? It was the first time I got mad because somebody killed my mom. Now, it was very bad. Anyways, I had a problem with it. First, it was the mother didn't want to die, didn't want to. Anyways.
If you really want to go back, it was really the Jedi's fault for even agreeing to train him in the first place. So it's really Qui-Gon Jinn's fault.
Sure, it probably is. Except I was powerful, I'll probably do it anyways. The prophecy will be fulfilled one way or the other. Now, let me ask you a question. I forgot my question. No, actually, yeah. Everybody that was and Costume also got a legal just for participating. Thank you very much. But anyways, second question. Somebody read the second question for us.
Why does the clothesline sag a little even without clothes on it?
Okay. So, how come the clothesline sags a little even when there's no clothes on it? So let's see.
That's still me.
Let's do you. Haley, why do the clothesline sags? Exactly. It's the clothesline has weight, right? It's not like it's weightless, and if there's not enough tension in it, it will sag, right? Very good. Oh my God. I can't. It's so hot. How does he do it?
I cannot do that. I'm so
It's more of a
sorry.
tattooed body than anything, so.
That's how he breathes.
Exactly, so it's not necessarily good, but.
No, it's because there's no breathing room for it. So like inside there.
The mouth consequence.
What? No, there is. And it's got. If you just, it's actually my sweat in my talking that's actually causing it to become hotter and hotter in there. You know what I'm saying? It's just. He has a machine to keep breathing. You know what I'm saying? And I don't. So
Just wear the helmet.
I'm gonna have the.
Yeah, you look more like a Snoop, so that's our hero. The other guys that no one cares about. Those are useless, you just get killed.
That's okay. I'll take one for the team.
Yeah, round of applause for me.
Is that straight?
Yeah.
Okay. Okay. The next question we'll ask is, if I can see this, if you're trying to keep something from falling off a cliff, right, by towing it, the spinning. Okay, so this is more friction. So we'll leave that for when we actually talk about friction next class. The only other thing I want to talk about is the normal force and how it's different in different situations. For that, let's come to the board over here. So, normal force is a contact force. It's a reaction force. It's a third law force. Okay. So when you put an object in a surface, right, that object will still have a weight. Now, remember how the second law works. The second law is summation of forces equals MA. Now, this is not a question, but you should still write this on your barrel ringer because we're doing this and you use it to study for the test. So you should still have this. Now, is this box sitting on the table like this binder that's sitting on the table over here? Is that accelerating right now when you're talking to this classroom?
No, it's here.
You need an hour and a half to do it. You're a little late in the period. You can't do that. You must sit and do the whole entire thing. Do you want to do the FRQ one? Oh, you have to do both together. You can't just, you can do it during lunch.
Really did commit to it.
It's really hard in there too.
Why don't you just poke holes in the side?
I love Chris Brown.
If I don't talk, it's okay. When I talk.
He dresses great.
You need to.
So much is writing on this one test, right?
Right?
Yeah, I'm going to
It wasn't that bad. Honestly, if you had studied the multiple choice practice, I told you to do it. A lot of the questions come from it. This is a.
No, the multiple choice practice that you put on, yeah.
Make sure you study that.
I did a lot for it. I did the questions with fluids. I just watched hella videos
There it is.
from that age.
What's your class number? Number one? You're going to set number one, okay? I don't have a Scantron right now, so you just answer it right here. Alright? Just set number one. Okay? The force is strong with you.
It really is.
You know that in the new movie, the hero is a black guy, right?
Yeah, I know.
Kind of looks like it.
A little bit, actually. They all look the same. I'm kidding. So, as I was saying, where's the piece of thought? All right, so, guys, please, over here. So, the box sitting on the table doesn't actually have any force acting on it. So, not net force acting on it, right? Because if it did, it would have to be doing what according to the formula? It would have to be accelerating or changing its pattern of motion. So if we just look at something sitting on a desk, what does that mean about the forces on it? If there are any forces on it, they must be what? Yeah, they must cancel each other out. So that means, but we already addressed that as long as you have mass and gravity is around, you're going to have weight. So the normal force is like the force that explains why it's not moving around. the table must be stopping it from falling, right? And that is the force that's acting on it. And this just represents the center of mass of the object, but it's really here, right? It's the contact force between the two of them that pushes back on it with exactly the same force of gravity. So if you were doing a dynamics equation for this object, you would find that weight minus, well, if you call up positive, down negative, you would call normal force minus the weight equals 0, because acceleration is 0, right? So if the acceleration is 0, you don't have any acceleration. That means the normal force in your situation is the weight. Now here's where it gets interesting. Apparent weight, so remember this is important. Apparent weight is the normal force. So the apparent way you feel, or how heavy you feel, is a normal force. So somebody tell me a situation in your life where you felt lighter. All right? Swimming. Very good. Swimming. All right? Something else. Oh, raise your hands. Yes. When the elevator starts moving in certain direction. Let's think. Gary, I want you on the first table right here somewhere. So, you can sit between the two of them right here. Yes?
Free fall.
Much less aggressive. Free fall is very good. Make sure you write these examples down. The examples of times where the normal force, where you feel kind of lighter than you're supposed to be. So we already did the pool, free fall, elevator. Now let's think about the elevator. So I'm saying an elevator, and it starts moving up. Do I feel heavier or lighter? Heavier. We'll think about that in a second. So when do you feel lighter? When the elevator starts doing what? Starts going down. All right, so think about that. We'll go back to the elevator in a second. All right, what else? Come on, let's think about it. Yes. Hold on, Jennifer. On a roller coaster, what part of the roller coaster do you expect? Right, exactly. On the bottom, you feel heavier, right? But at the top, when you go like, oh, you feel lighter, right? Now, people's reaction is saying it's because the roller coaster is throwing you up. It's not really throwing you up. It's just that you want to keep doing what you're doing, right? There's inertia, right? So you want to keep doing what you're doing. But at the same time, the roller coaster is going down. So what happens is that you're going up, the roller coaster starts to go down. So the contact between you and the cart and the roller coaster, so this is at the top of the roller coaster, right? The roller coaster starts accelerating downwards because of the friction with the track, right? But you're not on the track. The roller coaster is on the track. You're attached to the roller coaster by the weights. But until the weights act on you, or not the weights, the harnesses act on you, you actually want to keep doing what you were doing. And so your velocity is something like this. So that means that because of inertia, you're going to keep doing what you're doing when the roller coaster falls behind you. Which means that point of contact between you and the surface of the seat, what happens to the normal force? Think about it. What happens to it? So the roller coaster is falling underneath you, and you keep doing what you're doing. What happens to the contact? Yeah, you lose the contact. So you lose the normal force if you're weightless. Because normal force is the apparent weight. The way you feel is not gravity pulling on you, because when you're on a free fall, you don't even feel your weight. Right? So, for example, there is I should show you this. I will when you guys make practice. I'll look one up and I'll show you guys. There's an airplane that you can go into that's like a ride. And the airplane does this kind of thing, where it goes up and down and up and down and up and down. And you inside of the plane as it's doing that. Every time the plane is doing one of these, it's basically in free fall. The plane is falling. But you're inside of a room that's falling. Are you with me? So everything is falling around you, including yourself. And so you feel weightless. That is why astronauts are also weightless in the orbit. Not because there's no gravity acting on them, but because the floor of the space station is actually falling at the same rate they're falling. And so there's no contact between them and the floor. It's the same thing as the elevator when it starts going down. Does that make sense to you guys? So the apparent weight is actually, when you're hanging by a noose, hopefully you never have to experience that in your life, but if you're hanging by a noose, it is that force pulling up on your neck that you're really feeling. When I punch, everybody's, right, that's something else. That's something else. All right, but do you guys understand what I'm trying to say, what apparent weight is? So let's do one last thought about this, and then you guys go through practice. Let's say I will put the box now in an inclined plane, right? So the box is on an inclined plane. Now, if you think about it, the weight of the box is still going to go straight down. But if you think about it, part of that weight is going to act against the surface, and part of the weight, I'm going to split it into vectors, into components basically is what I'm doing. Part of the weight acts parallel to the surface. Are you with me? This part of the weight will pull the object down. That part of the weight will keep it connected to the surface. Does that make sense? Now, when it comes to the normal force is a reaction force to whatever contact the object is making with the surface, which means the normal force will be equivalent to that component, which we can call, say, weight Y, and we'll call this weight X. Are you with me? Which means in this case, the normal force equals the weight Y. Now, is the weight Y the entire weight or a fraction of the weight? Which means, will you feel lighter or heavier when you're going down like this? Lighter, because what you feel is always the normal force. So going down an incline, you also make. You ever drove a car really quick down the incline plane? When you do that, it also gives you that sense of weightlessness. So either way, weightlessness or the feeling of a reduced weight happens because of lack of contact. One more thing I want to say about the normal force before we move on is that it's not a vertical force. Now, yes, it's always perpendicular to the contact that you're making with the surface. So if I am doing this, is there a normal force there? Yes. Otherwise, I'll be going through the wall. I can do that too. Never seen in the movies, but it's a very special power. I will not demonstrate it right now because, I've got things to learn. But you can go over the wall by canceling the force that's acting on the wall, right? Very elementary, really. It's just if you know the ways of the force. But anyways, going through the wall, it's impossible in real life, right? Because the wall pushes the forces backwards, and that's the normal force. Does that make sense? Last class, I explained a little bit about that contact force business. Let me just talk about that really quick one more time. If I have a mass m here and a mass 2m here, and let's say we have a mass 4m here, all of them are traveling together, which means they're going to have the same acceleration. All right? Think about it. It's impossible for them to have different accelerations. Does that make sense? Because they're all pushing each other. They can't have different accelerations. So they're traveling together. All of it because there's a force pushing on this. Now, if I'm asked to rate how these forces here, the contact forces that exist between them, now remember, they're all third law pairs. Because this one's going to be pushing that one, which means that one pushes back on that one. That one pushes that one, which means that one pushes back on that one. Does that make sense for you? Right? Now, if I was not trying to rate them, well, think about it. The force that's acting on this one has to be 4 MA. Why 4 MA? Because whatever force it is, it's causing the acceleration of A for that object with its mass of 4. But that force that's pushing that here is actually pushing this one and that one. Does that make sense? We'll call this, by the way, the fourth contact force 2, and we'll call this contact force 1, and this just the big force. So here it's pushing the whole thing. So that contact force 2 has to be 4A because it's pushing a mass of 4m with an acceleration of A. This one here is pushing this ms plus that 4ms. Does that make sense? Which means force 1 has to be 5ma. Does that make sense? Now, this one here has to push the 2m, the m, and the 4m. Does that make sense? Which means the big one is going to have to be 7ma. Now, if you think about what fraction of the big force that contact force is, it's basically going to be 4 over the whole. This mass is what determines the fraction of the whole that contact force takes. Right? Because it's what it needs to take. It's the mass that force is acting on. And since that force is only acting on this, now this force is acting on both of these. Well, it's really acting on this, but if it acts on this, it also has to push the other one. So that force has to be 5ma. All right? This is important. And this is why last class I talked about it matters which way you put it. Because if you change the order of this, the contact force will be different, which is why the whole thing of pulling the max and which one, where it will snap, or which way to drop the hammer, made sense last class. If you forgot how that went, just watch the video and we talk about it. For the rest of the period, practice the ways of the force. There is, by the way, a lab on this apparent way stuff that's called Elevator Apparent Way Lab. The first part of it is supposed to make some predictions. Then you get a little scale and an object you can put on it. Then you go to security, ask them for the key for the elevator. go inside the elevator and you tape yourself going up and down 3-4 times and watch what the weight is doing with the scale. After you made the predictions, and then you qualitatively talk about if you're right or wrong about your predictions about what's going to happen to the weight. Because remember, the scale doesn't actually measure your mass. It measures the weight, and the computer just divides it by gravity to get. Which, by the way, think about that. One last thought. Think about that. Scales measure weight, correct? With what G? Right? Because G changes across the surface of the Earth. So technically, depending on where you go, the G is slightly different. So the scale might be giving you the wrong mass. Because if that scale came, say, from New York, and it was standardized there with a 100 gram standard, are you with me? By the time you get here, it's not 100 grams anymore, which is why you also have to zero the scale before you use it. So they send the scales with these little weights. You're supposed to put on it and zero it so that the scale knows what 100 is. What was I saying? Because the scale has to get the G of this location. That's very interesting how the scale does that. Anyways, that's a cool lab to do, and you also have other things to do. Remember, you have to get points between last class and this class, and it's going to count against you. All right? Have fun, guys.
How many points?
Elevator signing up.
I want to record you teaching.